refreshing spring break. This is homework 6, which has just been released. And we are going to walk through the assignment right now. Again, this homework is going to be due next Wednesday at midnight. So there are 2 ways to submit. You have to submit 2 parts, just like with all the other homeworks. The written part is to be submitted to Gradescope. So check Gradescope. You're going to see a homework 6 fun with graphs on Gradescope. So please make sure you submit the written part. And there's also a coding part, and this one is fun, very fun, very fun, very fun. You're actually going to be implementing your midterm exam. So you're going to have a lot of fun with this one. This also needs to be submitted to Gradescope, and you're going to see homework 6 code. There is an auto grader here that will grade all your assignments. That is worth 40 points, okay? So you really want to make sure you submit this. You can submit it in either C++ or Python. We actually have both options available for this assignment, so feel free to submit in whichever one you prefer. Anyway, let's go ahead and get started. So the first exercise is just reviewing some depth first search basics. All right, so we have depth first search. So in class, we saw how to use DFS to do a topological ordering of the vertices, right? So if you remember, topological sorting is an ordering of vertices such that if A comes before B, then there are no edges from B to A, right? So that is what a topological sorting is. It says if A comes before B. So for example, let's say here, let's say our sorting was BA. Let's say we tried to say for this graph, the topological sorting is BA. You'll notice this is not a valid sorting, like BA, C, D, E, let's say. This is not a valid sorting because a valid topological sorting is only the case if A comes before B, so in this case, B is before A, right? Then there are no edges from B to A. So in this case, there must be no edges from A to B, but we actually have an edge here, right? Intuitively, what this means is you can't install B first because it has a dependency, right? Like A is a dependency of B. Like if this arrow meant, this is what B depends on A, or A needs to be installed before B, right? And so that's what the directed arrow means. Then that means any sorting, any topological sorting for this directed acyclic graph would have to start with A. Well, recall that you can actually run DFS to figure out what the topological sorting is. So that's actually what we're going to do in this exercise. So let's jump to part 1.1. So this is saying run DFS starting at vertex C, breaking any ties by alphabetical order. Okay, so that means if you can go to A or D, you would go to A, okay, because you want to break by alphabetical order. So let's do that. So 1.A part A, you start at C, and really C can either go to D or to E, right? These are the only outgoing edges. We break ties by alphabetical order, so that means we go to D first, right? So we're going to go from C, then we're going to go to D. From D, there's only one outgoing edge, which is going to be E, right? So we're going to go from C to D to E. And then what's going to happen is we're going to pop back into D, right? Because we're done with E. So we go back to D. Then we're done with D because there's nowhere else to go. We already visited E. So we go back to C. And then actually we're done with C because there's nowhere else to go. So what we do is we actually restart the DFS, right? So first you do C, D, E, and then you pop back out all the way to C. And then you restart the DFS in the next unvisited node. So the next unvisited node is actually A, right? Because we're going to do them alphabetically. So we would go to A next, and then from A we go to B, and then we notice that everything has been visited. So this is the order. This is the order in which DFS would visit, right? So now if we look at each thing individually, we would say, well, for C, D, E, A, B, if you remember with DFS, you actually have start and end times. Okay, so basically, when did I start that node? So for C, the start time is 0, right? Because this is the node we started with. So start time is 0. When we go to D, we start D at start time 1, right? So it was the next thing we visited. Then we went to E, which was the next thing we visited. So its start time is now 2. And then we finished E. So its end time is now 3, right? So you entered it at 2, and then immediately in the next step, you finished it. There was nowhere else to go, so you were done. You went back to D, and then D also finished, right? There was nowhere else to go, so now you finished D. So the end time for D is 4, and then you finish C, which means the end time for C is 5, right? And then similarly, once you start A, we started A after we finished C, so its start time is going to be 6. B's start time is going to be 7 because we went to B next, and then we finished B. So that actually means B finished with end time 8, and then we finished A, which means A finished with end time 9. All right, so knowing this, the first question asks you, what do you get when you order the vertices by ascending start time? So that means 0, 1, 2, 6, 7. So we actually get C, D, E, A, B, right? So we're sorting them by ascending start time. So we're looking at the start time. So basically, in what order did you enter the nodes, right? Now that's what do you get when you order the vertices in descending finish time, okay? So now we're looking at the end time / the finish time, and we want to go descending. So we're going to start with the biggest one. So we actually start with B first. Start with B first. Actually A first, because A is the biggest finish time. Then we went to B. That's next. Then the next finish time is 5. So that's for C, then D, then E. So you get A, B, C, D. Cool. So that's basically question 1.1. This is how you do it. And question 1.2 asks for the exact same thing, except you are going to do it in reverse alphabetical order, right? So if you remember, for part A, we ran, for part 1.1, sorry, we ran DFS CDE. So we went CDE, and then we had to pop back out to A and went to B, right? So that's how DFS ran, and that's how we got all these start and finish times. For 1.2, you're going to start at C again, but now you're going to break ties in the opposite order. So instead of going to the smallest or the letter that appears in the alphabet earlier, you will go to the letter that appears in the alphabet later first. So you start with C and then you go to E. You see that? Because we could go to D, we could go to E, but in this case we go to E. Now E is done, so we're done. We go back to C, right? Now C is not done yet because then we still have to go visit D, right? This is how we do that, okay? And then you would pop back out and you would actually start with B first. And then B is done because you already visited D, you already visited C. So you pop back out because you're done with B and you visit A, right? So again, for this, you would set up a similar thing here. You know, you want your start and finish times. And you would say, well, C starts at 0. Then we went to E, actually. So let's change this. Then we went to E, then D, B, A. So then we went to E. So that means, you know, its start time was 1. See, we don't have a finish time yet. Then we actually finished E, right? So actually the finish time for E is 2. Then we came back to C, but we didn't finish C. We went to D first. So D's time is 3. And then D, then we finished D because we were done. So now the D finish time is 4. We went back to C and then we finished C. So C's finish time is, let's say, 5. Then we went to B. So its start time was 6 and we actually finished it immediately because there was nothing else to do. So its finish time was 7. Then we went to A. So its start time was 8 and then we finished it immediately. So this is the numbers you get, but the question, again, the questions are going to ask you, what do you get when you order the vertices by ascending start time? So 0, 1, 3, 6, 9, so you get this. And then what do you get when you order by descending finish time? Okay, great. So for part 2, we're looking at the world of graphs. And basically this is just asking you for like, how can you come up, how can you represent different problems as graphs, right? Because we're going to be spending a lot of time covering graph-based algorithms that run on nodes and vertices and edges, right? So they run on these abstract concepts, right? Like you don't see edges just lying around in the real world, right? You don't, or like not the kind of edges that we're talking about, right? So everything is very abstract, right? So DFS, BFS, we're about to cover Dijkstra's, other graph algorithms only run on the abstract concept of like a graph, right? So they need nodes and edges, right? But in the real world, you usually don't have nodes and edges. You have students, you have classes, you have cars, you have buildings, you have travel times, you have like difficulty, dependencies, right? You have relationships. Like those things aren't graphs per se. So a lot of the interesting problems that you would solve in the real world aren't immediately graphs. You have to convert them into graphs. So that's what exercise 2 is going to be looking at, is like how to convert real world problems into graphs. So then you can use the graph algorithms you're learning to actually solve these problems, right? And some of these we sort of covered in lecture, so I won't spend too much time on these. But basically, the main question that we're asking for is for each of these problems, try to formulate this as a problem about graphs, okay? So what that means is you need to tell me what are the nodes, what are the edges, okay? Is it directed? Is it weighted? Okay, like these are the questions we need to know about graphs, right? And then what we also ask is you want to figure out, well, what algorithm would you use to try to solve this problem? Okay, so like what algorithm? So given your graph, what algorithm would you use, right? So these are the questions you're looking at for each of these. So let's try, all of these I think we sort of covered in class. I think, if you really need a reminder, I would encourage you to take a look at, let's see, probably lecture 16, applications of depth first search, and lecture 17 or 18 are probably really good reference points for these problems, okay? So I'm not going to cover them in the walkthrough, but you should get, take a look at those lecture notes, take a look at those slides. I think they will help you out a lot with this problem. Okay. Here we are being asked to run Kosovo's algorithm on this graph. So you want to make sure you understand Kosovo's algorithm. This is the algorithm for finding strongly connected components. So Kosovo's algorithm for strongly connected components. And we actually covered this right before spring break. So if you need a refresher, you would head on over to strongly connected components. Lecture 18 or lecture 19 are both pretty good reference points for this homework exercise here. So let's open that up just to take a look on our end. So if we look at lecture 18 here, we can scroll down and we'll actually get to Kosovo's algorithm. So this is this guy, he's Kosovo, and here's the algorithm that runs in linear time. So the algorithm is actually pretty straightforward. So let's copy that over here so we can talk about it in more detail. Let's reorder this so it looks a little better, and let's discuss. So basically what we do is we're going to run DFS to create a DFS forest. We're going to choose the starting vertices in any order. So actually, if we go back to the homework assignment, we'll see that we are given a specific, we are told to break any ties by alphabetical order. So if there are ever two possible nodes you can go to next, you want to break these by alphabetical order. And as well, we are asked to remember that if DFS has reached a node with no unvisited children, so it can't go any further, then it will resume the search at an unvisited vertex, okay? So we'll decide which unexplored vertex to continue DFS by alphabetical order. So basically, anytime you have to make a decision about what vertex to go to next that is not obvious, right? Then you would do them in alphabetical order. So let's walk through here. Question 3.1 actually runs us through the first part of Cassidy-Juice algorithm, which is to do DFS and keep track of the finishing times. So actually here we're going to keep track of both the start and the finish time. So we would have node A, B, C, D, E, and your task is just to complete this chart. So again, we are told to start with node C so that its start time is going to be 0. You can see that C here has a couple of options that can head over to D. It can also go to A, and it can also go to B. All these 3 options are perfectly valid for a depth first search, but in order to make grading this question a little bit easier, we're actually going to be asked to break any ties by alphabetical order. So that means we actually go to A first. So A is the next node that we go to, so its start time is going to be 1. Now from A, we've already been to C, and we actually can't go back to C. The only one we can go to is B, following this edge from A to B. So B's start time would be 2. And then once we get to B, you notice that we actually have nowhere else to go. Can't go to C because this is an outgoing, this is an incoming edge. And the only edge that's outgoing is back to A, which we've already visited. So actually, this means that we're done with B. So we would mark the finish time for B as done. We head back to A. Again, A has nowhere, we already went to B, it's already visited, and we can't go back to C. So A is done. We mark the finish time as 4. And then we're back at C. And here we're, again, we could go to A, we could go to B, or we could go to D. We already went to A, we already visited B. So the only remaining option is to go visit D. So D will have start time of 5. And from D, we can actually head on up to E. So we'll visit E next, start time of 6. And you'll notice this is the last node in the graph. So we immediately finish with a finish time of 7. We pop back out into D, and then D has nowhere else to go. So D finishes with a finish time of 8. And then we pop back into C, and then C finishes with a finish time of 9. So that should give you your start and finish times for DFS, which is, essentially what this what this is expecting you to do. Now for question 3.2, again, so by the algorithm, we first do DFS to create a DFS forest. So actually, in our case, we didn't really even create a forest. We just had a single component. Because if you notice, we started at C. This has, C has, let's try to make this a little better. So C has 2 children, actually, A and D. These are the ones that we went to directly from C, right? Because B, we actually, even though there's an edge from C to B, we didn't follow that edge when doing DFS. We actually got to B from A. So we noticed that A had 1 child, which was B. And then D also had 1 child, which was E. And this actually, then eventually we came back up and we popped out of this tree. So this is what this is what we would call our DFS forest. But really, it has 1 tree. Okay. So the first step is to run DFS. Then the next step is to reverse all the edges, right? So you want to largest finish time and the reversed graph. So you want to reverse all the edges. So now you got to remember that you're thinking about the edges going in reverse order. And we're going to run DFS. And again, this is going to ask you, what do you get when you order the vertices by ascending start time for the second DFS run? So what we would do here is, again, let's keep track of our start and finish times. So this is for 3.2. And we are going to run DFS, but we are going to start on the node with the largest finish time, and we're going to reverse the edges for the graph, right? So the largest finish time here that we have is C. So we're actually going to start with node C again. So its start time is going to be 0. And let's delete some of this stuff. So its start time is going to be 0. And then again, you have to remember the edges are reversed. So actually, there is no outgoing edge to A, actually, and there's no outgoing edge to B, and there's no outgoing edge to D. Actually, all of these are reversed. They're all pointing inward. So actually, the only outgoing edge is actually the one going to E, right? Does that make sense? So we'll go from C to E. So then E's start time is going to be 1. And then we'll go from E. Again, this is a doubly directed edge, so E can get to D. So we'll go to D's start time as 2. And then D, obviously, again, we can go to C, but we've already visited C, so we wouldn't go to C. So we basically pop back out of this area. So that means D actually finishes with a finish time of 3. Then E finishes with a finish time of 4. And then C finishes with a finish time of 5, right? So now the next thing we want to do is we have nowhere else to go, right? So again, these edges that we see here, these are actually reversed. So they're actually incoming into C. So we can't get from A to B. So what happens is actually DFS just starts at the next highest node. So C, E, and D have already been processed. So that means C here is gone, D is gone, and E is gone. So the next node with the highest finish time is actually node A. So we would start at node A here. And we'll notice that C is already visited, so we can't go to C. The only node we can get to is B. So A's start time is going to be 6. Then we're going to get to B, whose start time is 7. And then we're basically done with the graph. So its end time is 8, and its end time for A is 9. So this is what the second DFS looks like. And again, you can imagine it does create a DFS forest, right? So this is going to be helpful to take a look at this. So again, we create a new DFS forest. We start it with C. And in this case, C actually had only one child, which was E. And then E had one child, which was D. So we had C went to D, who had one child, who went to E. So this is one of our forests, one of the trees in our forest. And then we had another tree that actually started with node A that had one child, which was node B. So it actually went from A to B here. And these are our 2 trees in our DFS forest. So we actually have 2 trees in our forest in this case, right? So that's for section, 3.2. It does ask you to run DFS, the largest finish time in the reverse graph. And then it asks, what do you get when you order your vertices by ascending start time? So we just need to look at the start times here and sort them in ascending order. So you'll actually get you get C, E, D, A, B, right? So C is 0 start time, and you sort them in ascending order. Cool. And then the last question is, what are the strongly connected components in the graph? So again, if you look at the definition of our algorithm that we started with here, we run DFS, we keep track of finish times, we reverse all the edges, we do DFS again, we create another forest, and then the strongly connected components are going to be the different trees in the second DFS forest. So it should be pretty obvious what the different trees are here. The last piece is we're going to look at question 4 here. So this is actually a pretty interesting question. It's very real world, very applicable to the real world. And one thing that I'll hint at here is you want to use Dijkstra's algorithm, okay? You want to be really familiar with Dijkstra's algorithm. So I encourage you to look, I believe, at lecture 23, I believe, is the one where we covered Dijkstra's algorithm. So you probably want to review that lecture just to make sure you can get this problem. So again, what we're doing here is you're planning an exciting trip from a town S to a shiny new city T. So we're trying to get from S, let's say, to T, right? So there may be many nodes in between, but we're going from S to T. You created a directed graph, GV, where each node represents an airport, and each edge represents a flight connection from one airport to another, right? So we basically have a graph where it's, we start at San Diego, and then from San Diego, you can fly to Las Vegas, right? So that's one flight. And then from Las Vegas, you can actually, from Las Vegas, you can fly to LA. From Las Vegas, you can also fly to, I don't know, Raleigh, right? So we essentially created a graph where each node is an airport and each of the edges correspond to flights that you can take from one airport to another. In addition to that, we have a value for each edge. So actually for, between 2 airports UV, we have a value, let's call it the weight of that edge, UV, which is equal to the probability that this flight is canceled. Okay, so again, if the weight from, let's say San Diego to Las Vegas, let's say this weight is 0.9, then that means, probability that the flight is canceled is very high, actually. It's 0.9 probability. So that means that flight is probably going to get canceled. So you don't want to take that flight. Well, I mean, you might if it's the best, but maybe you don't, right? So what we want to do is again, like we said, the original problems we want to get from S to T. So let's say we want to get from San Diego, because that's where we live, and we want to go, to Greensboro. And we're essentially trying to figure out what's the most reliable path. So that's actually what question 4.1 is asking, which is like, what is the most reliable path? Okay. So here we talk about we can measure reliability of a path as the probability of having all the flights in the path not being canceled, right? So what does that mean? That means, if we start at San Diego, and let's say, we first fly to Las Vegas, and then we fly to Nashville, and then from there we fly to Raleigh, and then we fly to Greensboro, right? So this is our path. You have 1, 2, 3, 4 different flights, right? For each flight, you're going to have the probability that it's canceled, right? So the probability, the weight from San Diego to Las Vegas, let's say the probability that this flight is canceled, 0.1, 10%, right? You're also going to have something from Las Vegas to Nashville. Let's say this flight is actually, it's canceled pretty often, so like 0.8. And then you're going to have, the flight from let's say Nashville to Raleigh, and this flight basically never gets canceled, so the probability of canceling is 0. And then you're going to have a flight from Raleigh to Greensboro. And again here, let's say this flight gets canceled every now and again, so let's say the probability is 5%. So, its weight is 0.05, right? What we want to do is we want to say, well, suppose we decide to take the flights along the path P with K flights given by E1, E2, all the way to EK, right? So these are each of these flights: San Diego to Las Vegas to Nashville, Nashville to Raleigh, Raleigh to Greensboro. How reliable is this path using these probabilities, right? So this probability is going to be P E1, this is P E2, P E3 because it's my third edge, and then P E4 because it's my fourth edge, right? So this is one, this edge here is E1, this edge here is E2, this is E3, and this is the fourth and final flight, which is E4. So we have probabilities for each of them. And then what's the overall reliability of the entire path, which really means what's the probability of having all the flights not being canceled. So what's the probability essentially that my itinerary is successful, right? That they are all not canceled. So these PE1s give us the probability that they're canceled, right? So the probability that this flight succeeds, the first flight, is actually 1 minus 0.1, right? Now, in order for my whole itinerary to succeed, my first flight has to succeed and my second flight has to succeed. So assuming they're independent events, we actually just multiply them together, right? So similarly, for my Nashville to Raleigh flight, I would say 1 minus 0, which is just 1. And then my Raleigh to Greensboro, I would say 1 minus 0.5, right? And then what we can do is we can generalize this, right? This is a specific example, but it's not too hard to just generalize it by saying, well, 0.1 is PE1, 0.8 is PE2, 0 was PE3, and 0.05 was PE4. So for an arbitrary path, it looks like what we do was just we multiply all the probabilities of canceling. We do 1 minus the probability it gets canceled because that gives us the probability that the flight succeeds, and then we multiply all of them together along the path. Okay, so that's what we're expecting for 4.1. And then for 4.2, it says, create an algorithm to find the most reliable path between S and T. By most reliable path, we mean that the path P you find from S to T should have the highest probability of having all flights in P not being canceled. Okay, so having plenty of time for the trip, you do not care about how long or how much it takes to travel. but you want to reach the destination with exactly the route you planned. Okay, so here's a couple of hints here. So we're essentially trying to find for 4.2 the maximum probability flight plan from S to T. Okay, so this should remind you again, I kind of hinted at this. Take a look at Dijkstra's. Okay, so what does Dijkstra's do? Dijkstra finds minimum, right, shortest path from S to all vertices, right? So again, you can see like, hey, maybe we can modify Dijkstra's to help us find this maximum probability thing, right? So let's take a look at the pseudocode for Dijkstra. So let's just open up, again, I believe lecture 23, actually lecture 22. So if we open up the slides here, we'll see that Dijkstra's algorithm, we can actually scroll down to the pseudocode. That might be the easiest thing to consider, which is here. I'm having a hard time copying that. Let's open up the actual slides. Scroll down to, let's find the pseudocode because that's the most helpful. Here, right? So here's the pseudocode. Again, having a hard time, but you know what? Let's just look at it. Let's reference it and let's see how this can help us. So again, Dijkstra find the minimum shortest path from S to all vertices, right? And the way it works is, step one is set all vertices to not sure. So that seems like we might keep that step. Step two says set the distances, the estimate, and overestimate to all vertices to infinity for all V in V, right? So our question here would be, since we're trying to find the maximum probability, is infinity the right value to set this to, right? So again, one thing to notice is that when we take the minimum of the very first time, the reason we choose infinity is because it's a clear overestimate of our reliability. And what we're trying to find here is we're actually trying to find the path with the maximum reliability. So we actually want to have clear underestimates of the reliability. So in fact, we would set dV to 0 for all V in V, right? Because an underestimate for our reliability is that in order to get to any path, it's actually impossible, right? 0 probability chance. They're all impossible. Then we have here, if we take a look again, let's try to zoom in. Oh, can't zoom in. Very interesting. Yeah, let's try to zoom in maybe 200%. We'll see that the next one says to set the source to 0. So again, the reason we set the source to 0 in the original Dijkstra's is because we know that the shortest distance from S to itself is 0. But in this case, we're talking about maximum probability flight plans, right? So the flight to the city itself actually succeeds with probability 1. So we would set ds to 1 in this case. Does that make sense? Great. That's fantastic. And now we continue. So the next step is like, while there are not sure. Let's zoom out a little bit. I don't like having zoomed in so much. Zoom about 100 again. Yeah, so we're looking here while there are not sure nodes. That seems like we'll keep that. We pick the not sure node U with the, and here we stay with the smallest estimate. So again, we're going from minimum to maximum. So actually here, what you probably want to do is you actually want to pick the most reliable flight that you can get to next rather than the smallest. So with the largest estimate dv, right? Then for v in u dot neighbors, sorry, so this is du, so pick the u with the largest estimate. Our update is actually going to be a little bit different because again, dv is no longer an overestimate of the shortest path. It is now an underestimate of the most reliable path, right? So for each of our neighbors, we're actually going to update dv instead of being the minimum to being the maximum, right? Because we started with an underestimate and we're trying to get closer and closer to the real value. of dv itself, or what is the reliability of getting from S to U times the probability that we are canceled, right? Sorry, the probability that this new flight from V to U succeeds. So this would be the weight from U to V, right? So we take all the flights from S to U first, right? That has this reliability. And then we multiply by the probability from 1 minus weight of UV, right? And then everything else kind of stays the same. We mark U as sure. And now, once we're done, we say that D, the reliability from S to V is given by dV. So now we have all the reliabilities, and what we're actually looking for is the reliability from S to T. So we can just say dt. Great. So at this point, you may actually be wondering, if we go back to the homework assignment, you'll notice that I actually give you this kind of hint here, which is kind of interesting, which says that the logarithm of a times b is actually equal to the logarithm of a plus the logarithm of b. And you'll notice that we didn't use that at all in this solution. So you might be wondering to yourself, like, wait, what does that mean? Or like, why would this be helpful? And I encourage you to pause the video and think about that for a second, just to really, I don't know, push yourself to see if you can see how that would work, right? Oh, the other thing that we're missing here is you want to justify that your algorithm is correct. So you want to make similar arguments that we did in lecture to like claim 1, claim 2, right? And then you also want to briefly analyze the running time. So you won't be able to do this yet. So any analysis that gives us, a general understanding of how long this algorithm is going to take to run is suitable, since we didn't actually get to cover all of Dijkstra, but we will cover it on Monday. So if you pay attention to Monday's lecture, that should help you a lot in sort of analyzing the running time, because at the end of the day, we didn't actually change things too much, right? We basically, changed the starting settings to different values, and then we changed the update rule from a min to a max, and we did some other stuff, right? So going back to this hint, if you spent a little bit of time thinking about it, you will notice that essentially, if we're going from A to B to C, then what we want to do is we want to compute 1 minus the weight from A to B times 1 minus the weight from B to C. And if you take the logarithm of this, actually, you'll notice that this is equal to the logarithm of 1 minus the weight of A to B plus the logarithm of 1 minus the weight from B to C, right? So in a way, you can convert this multiplication, right? So one thing here is we are trying to find the maximum, right? The maximum value out of all the possible paths. This is one path, A to B to C, and its value is going to be given by this, which we said the logarithm of its value is going to be given by this, right? And here we're trying to find the maximum V, okay? And we know that V is between 0 and 1, okay? So it turns out that the maximum V here is actually going to equal to the minimum. If we, again, so Dijkstra doesn't work on graph. So one thing to notice is if we just take the logarithm of these values are going to be negative, right? So if you go to the logarithm function, let's say here, right, log 2 of x, you notice that when the values are between 0 and 1, the logarithm is actually negative, right? And it gets negative pretty fast. So these numbers are negative for our graph, right? So intuitively, what I'm trying to do is I'm trying to say, well, like instead of the weight from U to V being, the probability PE, or PUV, like the probability that it is canceled, right? Instead of it being this, which is what we had in this original algorithm, I'm saying, well, maybe I can make a new graph whose weights are actually given by the negative log of 1 minus the original weights. Okay, so why do I do this? I do this because, as we saw above, if I'm multiplying 1 minus these original weights, right? So if I multiply 1 minus these original weights, if I take the log, that actually becomes addition in the logarithmic space, right? And not only that, but then if I take the negative of that, all of those weights will be positive, right? So essentially what I'm saying is that for a path, AC, originally I wanted to do 1 minus weight UV times 1 minus weight, 1 minus weight A to B, and then B to C, right? So this is my reliability for the path. Well, I'm saying that actually, instead of doing this, what I can do is I can do my reliability is given by W prime AB plus W prime BC, right? So now I'm just adding two edges, and not only am I adding them, I claim that these edges are positive, right? So my entire graph is positive edges, and I'm adding them, okay? And essentially what happens here is if we look at our definition of W prime, this is actually equal to the negative log of 1 minus WUV plus the negative log of 1 minus the weight UV, right? That's a pretty interesting trick. Again, by the fact that adding logs actually means you can multiply them, this is equal to the negative log of 1 minus the weight UV times 1 minus the weight, oh sorry, this is not UV, this is AB, this is BC, this is AB, this is BC, which is this value here is actually the reliability of A to C, right? So this is actually equal to the negative log of PAC, right? So again, we set the reliability from A to C is given by this formula, and you'll notice this formula is exactly the same, but here we're taking the negative log. So logarithm is actually a monotonic function, so it means that, like, the max of log x is actually given by the max of x, right? So wherever x is biggest, like if you're looking for the maximum argument, like what is the x that gives me the biggest value of log x? That's the same x that gives you the biggest value when you're just looking at x directly, right? So maximizing or minimizing the log is actually going to maximize or minimize the interior argument, right? And what we notice here is we're actually, originally here we're trying to maximize this value, right? So maximizing the log is going to maximize this value, and minimizing the negative log, right? So now minimizing the negative log of PAC, that's actually going to maximize the log of PAC, which also maximizes PAC. So in a sense, by doing this transformation where we set all of the edge weights, right? So what are we doing? The transformation is we create a new graph where now the edge weights are given by this formula, negative log 1 minus the weight of UV. Then we can just run Dijkstra, the original unmodified Dijkstra's algorithm. You can actually run it directly on this graph, and it will give you the, what it'll give you is it'll give you dv is going to be the, shortest. So you're still going to look at dt, and it's going to be the shortest path from S to T, right? But shortest, dt, that means it's actually going to be equal to negative log 1 minus P of, sorry, not 1 minus log of PST, negative log of PST, which means if you actually want to know the reliability, you can actually just negate it and exponentiate whatever answer you get, right? So going back to the homework, that's why this hint is given, because there is another solution here, which is basically instead of modifying Dijkstra's algorithm to take the max and do multiplication and then do all the stuff here and like modify the initial values, etc., you can actually just modify the edge weights. So make all the edge weights equal to this instead of the probabilities, and then just run Dijkstra as normal. And then you can find the most reliable path from S to T. Great. Now, question 4.3 is kind of interesting. This is kind of an open-ended question, so you provide many different answers, but it's actually talking about the fact that we've designed this, this is like a flight optimization algorithm, which is really cool. Now you can actually tell, everybody you've talked to, like you actually know how to do this, okay? You know the algorithms, you know how to code this up. You could work at an airline company and help them do this. But there's a lot of like ethical questions, right? And basically what 4.3 is asking you is just write a 1-paragraph memo to the programming team explaining why these or other values should be taken into account, right? So the only thing our algorithm takes into account right now is what is the most reliable path, right? Maximize the reliability of the suggested routes. But you're probably overlooking, maybe the most reliable path is really long, right? So that's time wasted, right? That's extra jet fuel, right? That's extra work from the pilots, right? Maybe, the most reliable path, always goes through one airport, right? So now that airport is going to be very congested, right? Maybe the most reliable path ends up going over Russia, right? And like, do you really want that? Like, especially in the current climate, right? So just, talk about like what are some other considerations, right? Like it's not enough just to solve the computer science problem, right? Like you really need to think about like how is this, if you implement this algorithm and you use it to recommend flights to people, is that really what you want to do? Like, are there other things you should think about before recommending flights to people about this, right? Like, are there other things you should optimize for that are not included, right? All right, problem 5 is the last one. This is pretty interesting. You actually only need to know BFS slash DFS for this. You need BFS. So you definitely need BFS, and you need to know, or like you don't need DFS, but you can also use it. For this walkthrough, I'm going to focus on just breadth first search and how we can use that. And essentially what we're being asked of here is, if we take a look, we are in a campground and there are going to be 2 groups of tents. There's exactly 2 groups. You don't need to worry about extra groups. We are given an M by N matrix A where 1 represents a tent and 0 represents an empty camping ground, right? So Aij is going to be 1 if there's a tent there. And Aij is going to be 0 if there's not a tent there. And we're guaranteed, so we're going to be given, like how to connect. So we're trying to implement this algorithm. We're going to be given as input A, which is the matrix described above. And the output should be the minimum number of spare tents that you need to build in order to connect these 2. So minimum number of tents I need to build to connect these 2 camps, right? So we have 1 camp here, another camp here, and you're looking for the minimum number of tents that you need to build. we are looking for an OMN algorithm, right? So OMN. However, do keep in mind that the grid itself, like the entire grid, is M by N, right? So OMN here, in this case, like OM times M, this is actually kind of like O linear, right? Because you can only look at each square like, once or twice or three times, right? You can't do a lot of work. So it's kind of linear, even though, obviously it has multiplication in it, but the input itself, like the entire grid of input is of size mn. So you really can only look at each item in the grid like once, twice, three times, okay? Yeah, so I can connect these two camps. You might locate all tents, and yeah, and then we also give you a hint, which is you may want to locate all tents in one connected collection of tents first. And basically, the only way you're going to get an algorithm that runs in OM time is you really need to run like BFS like once or twice, right? Or three times or something. If you're trying to do something super complicated, this is probably the wrong approach. So I encourage you to take a look at the lectures, head back to the breadth first search lecture, pull that up, and make sure you understand, some of the information around, the pseudocode for breadth first search. Right, so I think we did cover breadth first search a few times. And the pseudocode is here. So this is the pseudocode for breadth first search. Let's try to zoom in a little bit so we can see it a little better. And you'll notice that, let's take a stab. Let's try to use breadth first search first, but let's think about the problem a little bit too, right? So I encourage you to pause the video and sort of think through the problem, how you would solve this with a modified version of breadth first search, let's say. If you came back, then you want to follow the hint here, which is you might want to locate all the tents in one connected collection of tents first, right? So essentially what we're going to do is we're going to start by iterating over our input matrix to find a 1, all right? So for, I equals 0 to n, for j equals 0 to, so let's say this is inclusive, so n minus 1, m minus 1. Let's look at aij, and let's say if aij is 1, then that means we found one of the connected components, right? So what we're going to do here is we're actually going to try to find, as the hint suggests, the rest of the tents in this component. So the rest of the squares that have a 1 in them. And the way to do that would be to essentially run BFS at this point, right? So let's say we keep something, let's keep a visited array. And, let's start this as, same as A, but all false, right? So it's going to be the same as A, so same size, but it's going to be all false. So it's going to be a matrix, right? And what we would do here is if we have 1, then we would say, okay, run first BFS or DFS, whatever you want, starting at ij, right? So this is our node. Let's start at ij. And fill in this visited array, right? So mark the nodes that we've already been to as visited. Let's run the first DFS using the fact, like find, let's call this like find tent or find camp, right? So let's actually try to code that up. So find camp, let's say it also has A as input, so we give it A. Then we give it ij, and we gave it this, array or vector that's visited, right? So what we can do here is we can actually follow the pseudocode, right? So let's set li to the empty list for, for I equals 1 to ... n times m. So for every single possible node, we're going to say the level is empty, right? Then we're going to say L0 is equal to ij. So this is the first node we're going to look at, where w is the starting node. Then we're going to we're going to keep a visited array that we have here. So we're going to say, okay, well, I visited ij. Let's set that to visited. And then for I equals 0 to ... n minus 1 for u in li. And for each, right, so here are the differences for each v, which is a neighbor. So now we're looking at the neighbor. So what's considered a neighbor, right? So there's actually 4 possibilities for neighbors, right? You can either be ai plus 1 j, you can be ai j plus 1, or you can be ai j minus 1, or you can be ai minus 1j. So those are the 4 possible neighbors. And we're going to say you're a neighbor if there's a tent that's also there, right? So if aij equals 1, if aij equals 1, if aij equals 1. So this is actually just hard coding all the 4 neighbors that are possible. Then if they are equal to 1, so that is a neighbor, then we want to check if v isn't yet visited. So if, visited I plus 1 j. If not, so if I have not visited, then we're going to mark v as visited plus 1 j. We're going to mark it as visited. We're going to set that to true. We're going to add it to our right. So we're just running BFS here. We're going to add it to sorry, not add it. We're going to put it into L I plus 1. So let's say push back, I plus 1 j. So that's like at the next level, right? And then we're essentially, you repeat this and you change some stuff for each of your cases, right? So assuming that works out correctly, this is sort of enough. But also what we want to do is we want to find the camp, and something that's going to be helpful for us is we're actually going to keep track of all the empty spaces next to the camp. So let's say empty spaces next to camp, and we're going to make this into a list. Or let's make this into a set, right? So we just have a set here. And what we're going to do is if you are equal to 1 and if you're not equal to 1, so let's say else, I am going to, let's just call it empty. I'm going to add you. So I plus 1j, right? So I'm going to add you. And all of these, like you can imagine, this is I, this is j plus 1. So you have to change all these values to match the if statement. And then you do have this else. You're going to add, instead of I, you add j plus 1. And you do the same thing for the rest of these. I'm not going to repeat it, but essentially this is the idea. So what is this going to do? This is actually going to explore the entire connected component. So we know ij is a 1, and then we know that anything that's connected to it, we are going to go explore it. So this algorithm is going to take O of nm time, right? Because it's going to explore the entire graph and it's going to try to look for all the things that we are connected to. And it's only going to follow edges that are equal to 1, right? So it's only going to start with our immediate component, and it's going to follow edges that are 1, which are just, is there a tent next to me? And then once it gets to the end of the entire camp, right? So if there is not a tent next to me, all it does is it adds this, keeps track of this exterior boundary. But it does not add it to like the li plus 1, right? So it won't go visited afterwards. So that's the find camp algorithm. And we can say here's like exterior is equal to this, right? And then actually what I would do here is I would break, or well, yeah, I would break. And what I would do is I still have this visited that's still marked. What we want to do next is we actually want to run BFS again, but we actually want to start with all the exterior nodes as the ones that are keeping track of the length, right? So all the exterior nodes are exactly 1/10 away from being part of our camp. So the idea here is that you can imagine kind of expanding your camp, and we're going to keep track of that. So let's say, again, Li is equal to empty for I equal 1, 2, and m. And again, I'm looking at this code to reference this. We're going to set L1 as equal to the exterior. So let's, we make this into a list and we set it equal. So L1 is all the things that I can reach in one step, which is the exterior, which is actually what we just found before. And then we are going to mark the exterior as visited. Okay, so that's mark W as visited. We mark all the exterior ones as visited. And then we just repeat the rest, for I equals 0 to nm, for U in L, actually for I equal 1, for L in Li, and then for each B, which is a neighbor of U. So this is actually where it gets, again, a little bit different. So we want to modify this algorithm where a neighbor for us, in this case, is actually going to be adjacent spaces that are empty. Okay, so that's going to be a neighbor for us. So you can imagine doing something similar to this, where we check all 4 neighbors of U. So let's say this is IJ. We check all 4 neighbors of U. Going back, we're looking at the exterior from 1 to nm, and we look at each level. And now if ai plus 1 j equals 1. So again, what we're looking at here is we're actually considering edges where we are next to an unoccupied space, right? So that's when we actually have an edge, right? And you want to consider all 4 of them. You want to check to see if they are equal to 1, or if if they're equal to 0. So if they're equal to 0, that means it's a possible edge for you to place a tent on. So you do want to consider it. And you want to add that as your, level, right? So you would say if, this one, J is not visited, then mark as visited and put in L I plus 1. So this pseudocode here, again, like there's 4 other statements that you need to complete. It's actually pretty complicated, but I'm going to leave this incomplete for now. But if you do, something similar to this, then your Li, the other thing you want to keep in mind is you want to break out of this loop as soon as you have reached a value, which is if you look at all of your neighbors, and if they equal 1, so in the else statements of your if statements, so else, if they're equal to 1 and they're not visited, so else, if they equal to 1 and if, I plus 1 j is not visited, right, then that means it is not one of the original ones that you started with, right? Because we marked all those as visited when we did this first find camp call up here. You can immediately break, or actually you can immediately return I plus 1 as the answer, because that actually tells you that you have now built up enough tents where it only takes I tents in order to connect to the new unexplored region where you had it equal to 1. So this is the pseudocode. Again, I encourage you guys to think through that and really think about it. The running time, again, here, we do have these 2 nested for loops, but you can see that like this is at most going over the graph once, and then we actually break out of the for loop, right? So this is not nm times, find camp. So let's look at this one. So find camp is basically DFS, which means the running time is O of nm. Why is it nm? Because BFS, the running time is nodes plus edges. And in this case, the number of nodes, which is the number of squares in our grid, is equal to nm. And the number of edges is equal to 4 times nm. right? Because for each node, we have 4 edges. So they're essentially the same. So it means the overall running time is O of nm. So that's for find camp. So going back to our original algorithm here, the running time is O nm. And you might think, well, I have 2 for loops, so isn't that nm times nm? Well, no, because as soon as you find the first one, you exit out of this for loop. So even though you have 2 nested for loops, which themselves are O and M, this only runs once, right? Despite having the 2 for loops, because it's inside the if statement, and as soon as it runs, it breaks out of it. So at most, this whole section is going to be, O of 2 nm. So that's O of nm. And then similarly here, this is just BFS, right? A modified version of it. So again, by the same reasoning, the running time is going to be O of nm. And yeah, that looks good for 4.3. So let's go ahead and jump over to the coding sections. So again, if you want to get started on the coding, well, there's a lot of you working on this. Let's jump back to the dashboards and take a look here. I'm actually not going to go over the coding in too much detail in this walkthrough, since a lot of the coding here is really just you implementing the homework you've already done, or like the stuff you've already worked on for your midterm, right? So here you had me at sorted. Basically what this is asking you to do is to go to find missing, and I actually give you a helper function so that you don't have to copy your input around that has the start and the end points. So you're actually going to implement this function here. And I think just something to keep in mind with the pseudocode, again, because you're doing the input with start and end, then your length, you're not going to take the size of A, right? You're not going to do input.size, right? N equals. You're not going to do that. You're going to do N equals end minus start, right? This is what you're going to be looking at to do here, because that is the length of the array you're looking at, right? So the whole vector is going to be, 5,000, but you're only looking from index, 10 to 12. So 12 minus 10 is 2, right? Then the other thing to keep in mind as well is whenever I do A0 here, right? So this find missing is assuming that when you call recursively, you're actually, breaking down the array into a smaller subarray, right? And in C++, that's not what we're doing. We're actually using the start and the end values to tell us where to start and where to end at the thing we're looking at, which means that anytime you see an A0, that doesn't mean input 0, right? That actually means input start, because we're looking at the start position, right? Because we're starting on the start index. So if you do input 0, that's going to give you some issues, right? So that applies mainly for this one and also for the pseudocode here. Again, same idea. The length is actually the end minus the start, and then anytime you see an A0, you have to remember that we're looking at the subarray from start to end. So A0 really means a start. Similarly here, when you see the syntax that's saying sort of, look at the left half of the array, we're talking about the left half of the array that we're looking at currently, not the left half of the input, right? So it's not going to be, always look from start n divided, from start 0 to n divided by 2, because that's the left half of the entire array. But really, we're looking at everything between start and end. So the left half of that is going to be from start to start plus n divided by 2, right? Where n is the actual length of the subarray you're looking at. Now, for these other ones, these should be fairly straightforward. I don't think there's anything particularly tricky about these in terms of writing them in code. So I encourage you to take a stab at it, and best of luck.